So this is a video to explain the energy stored in the arrangement of charges on a capacitor, and in particular why we have that 1/2, which surprised us a little bit in class. So let's start with the story. In the beginning, we have two neutral plates that are wired up like a capacitor. So I've drawn them. And the very first thing we're going to do is to take a little piece of charge from the bottom neutral plate, and we're going to move it up to the top plate, as so. And now we have two plates that are very slightly not neutral. Now there's some potential difference between the plates. So now, if you want to move a little bit more charge, so we take another patch where it's neutral, and we're going to take this piece of charge and we're going to move it up there. Now we have to do some work. And the amount of work that we have to do to move that is just a little bit of work. It's equal to the little bit of charge times the potential difference that was already there. But when we do that little bit of work, the potential difference increases because we've changed the charge separation. So if we want to do a little more moving of charges, then we have to do a little bit more work, because each time this potential difference gets bigger and bigger, so the amount of work we have to do gets bigger and bigger. And because our goal is to find the total amount of work to create the whole arrangement of charges, we have to add together all these little pieces of work. And because all those little pieces of work are getting bigger and bigger and bigger as we add, we can't just multiply them normally, we have to integrate them. And so what we are really integrating is the energy to move each little piece. So there's the Q delta V that we have as our potential energy for generic charge arrangements. But we have a D because we have to move each little piece of charge against a changing potential. And so to solve for this, we need to figure out how to write this delta V in terms of stuff for capacitors and how to integrate over charge from no charge to the full charge. So I'm going to do that on the next page. So we know for capacitors, the definition of capacitance is the charge on the plates divided by the potential difference. So how much charge can you hold for every extra volt, the potential difference? And we can rearrange that to have an expression for the potential difference as a function of charge. For a capacitor, the potential difference is equal to the charge divided by the capacitance. So I'm going to plug that into our equation. Now the capacitance is constant. That means that it pulls out in front. So we have a 1/C, and we're going to integrate from charge being equal to 0 up to some maximum charge. If we integrate Q dQ, so what's the antiderivative of Q with respect to dQ? It looks like it would be 1/2 Q squared, right? Because we can check. So what's the derivative of this? That would be 1/2 times 2Q minus 1. So 2 minus 1 is that. So that gives us Q. Okay, so this is the antiderivative. So the integral would be 1/C times 1/2 Q squared evaluated from Q equals 0 to Q. And if we plug these limits in, it's 1/C times 1/2 Q squared minus 1/2 0 squared, which is 0. So that's 1/1/2 Q squared over C. Okay, so this is the energy stored. We can check that it has the right units. We have coulombs squared over capacitance. Capacitance is coulombs per joules per coulomb. So the coulombs cancel and we have joules, and that's correct. So one more page. So we have this expression that came from our integral 1/2 charge squared over the capacitance C, but we know that C is defined as charge over potential difference. So if we plug this into there, we get another form of this equation, which is Q delta V. So see, that looks like the energy of 1 point charge lifted through, or Q point charges, but we have to have the 1/2 to take into account the area part. This is an integral. We can do this one more time. So if we substitute in for delta V is Q over C. Oh, we already had that one. What's the third one? Q is equal to C delta V. So we could substitute in this one more time here and get 1/2 C delta V squared. So all of these expressions are equivalent to each other. So your equation sheet will have the energy stored in a capacitor. You can write it 3 ways. I think only 2 of them are on there, but they're all equivalent.